Some other interesting alkenes include oral contraceptives. These artificially mimic hormones which can prevent pregnancy. So the way that birth control works is you take the pill, it can thicken the mucus of the cervix, making it difficult for sperm to reach the uterus. So that's one way that birth control works. And that would be a norethindrone, which is the synthetic progesterone. So you can see that that one has an alkyne. Another alkyne is ethinyl estradiol. This makes the pituitary gland think the woman is pregnant, so they don't ovulate. So you can see the different methods for working there. So we have estradiol, which has the OH. That's a naturally occurring hormone, as well as progesterone. And so we take the functional groups and change them up a little bit, and it can have different effects on your body. So before the 1960s, women ingested rust, gunpowder, tree bark, sheep's urine, elephant dung, and other compounds in order to prevent pregnancy. So medicine has definitely come away from that. Reactions that we can do with alkenes include addition reactions. In this case, elements are added to a compound. In an alkene reaction, one of the bonds is a strong bond and the other is weak. The weak bond is the one that breaks and forms new bonds. And we can do these reactions with hydrogen, halogens, and hydrogen halides, and also water. So in an addition reaction, one bond is broken. So there's one strong bond and one weak bond, like we mentioned earlier. We add X and Y across the double bond. And we add X and Y to our compound. So two single bonds are formed. A summary of these reactions: one bond is broken, so there's no double bond there anymore, and we're going to form two single bonds. So for cyclohexene, we add H2 with a metal catalyst. That's going to add H's across the double bond. And you don't have to draw those in because they're implied, but I'm just drawing them to show what happens in the reaction. When we react cyclohexene with halogens, either chlorine or bromine, we get the cyclohexane back. So that double bond goes away, and when we're going to place those two hydrogens with whatever halogen we added. Cyclohexene with HX, we're going to replace one of the bonds with H, and the other one gets the X. So again, the double bond goes away, we get an H and an X across the double bond. When we react cyclohexene with acid and water, we're going to add, you can think of it as HOH. One carbon will get the hydrogen, the other one will get the OH. So we're going to form an alcohol in the process. So if we take a closer look here, hydrogenation is adding the H's across the double bond. So we get our alkene. So these lines can be any group. This is just a generic reaction. And with this reaction, we're going to add an H across the double bond. An example of this is with ethylene. We add H across there. And really, you could just draw this to show the H's are all there. Or if you want to see the hydrogens being added, you can draw those in. So H2 is added across the double bond, and we form ethane. So here we're going to draw the product of the following reaction. H2 is what we're adding. Palladium is a metal catalyst that helps the reaction to proceed. We're going to keep our carbon skeleton the same. And you can draw it this way, which is totally correct. Or if you want to see what is happening in the reaction, you can draw your hydrogens in. And here's a couple practice problems, the same type of thing. You can draw in your hydrogens, or you don't have to. Your carbon skeleton stays the same. And draw in your hydrogens, or you don't have to. In a halogenation, we're going to add halogens across the double bond. And that halogen can be chlorine or bromine. So there is an example right there where we're adding the chlorines across the double bond with Cl2, and Br2 we're going to add bromine. And sometimes halogenation with bromine is used as a simple chemical test to determine if a double bond is present in an unknown compound or not. So if we have hexane, we add bromine to that, and it does not change color because the bromine doesn't react to that. So Br2 is present. And in hexene, the Br2, there's no color in the flask anymore because Br2 has reacted. And so it is colorless. And that's how we know there's an alkene present. If we add a hydrogen halide to a double bond, we're going to add a halogen to one carbon and the hydrogen to the other. So with ethene, we get H added to one side, Cl to the other if we add HCl. And with HBr, we add H and then Br. So this, if we were naming it, is chloroethane. And this is bromocyclohexane. If an alkene is asymmetric, so it's not the same on both sides, the hydrogen is going to go to the carbon with more hydrogens. And the X is going to go to the carbon that's more substituted. So X goes to the more substituted carbon. So in the example with propene, this is not symmetric. The first carbon here has two hydrogens on it, and the second one has only one hydrogen. So here's my carbon skeleton. The hydrogen is going to the carbon with more hydrogen, so it can be surrounded by its friends, and the chlorine is going to go to the other side. This is 2-chloropropane. So we don't form 1-chloropropane. And if we're adding HBr across the double bond, my carbon skeleton is going to stay the same. The H is going to go to the carbon with more H's, so this had two H's before, and the bromine is going to go to the more substituted. So this carbon here has a bunch of carbons coming off of it versus the other side there. As we look at hydration of a reaction, this is adding water across the double bond, or HOH. So we're going to see an H added to one carbon, OH added to the other side. So we're adding water across the double bond. And in ethylene, we have two carbons. One gets an H, one gets the OH. So this makes ethanol. Ethanol is sometimes added to gasoline as an additive because it can combust to form carbon dioxide and water, which reduces a great deal of energy. And even though ethanol can be formed by the fermentation of carbohydrates in grains and potatoes to make the alcohol that's in wine and beer, most of the ethanol that's used in gasoline comes from the hydration of ethylene and not from yeast. So just like in the case of hydrohalogenation, if we have an asymmetric alkene, the H is going to go to the carbon with more hydrogens, and the OH, or the other group, will go to the carbon that's more substituted. So in this case, with propene, we'll see the same carbon skeleton. The hydrogen is going to go to the carbon that has more hydrogens, and the OH goes to the more substituted carbon. In the case of the cyclohexene, our carbon skeleton stays the same, and then we're going to add our OH to the carbon with more carbons, and the H to the carbon with more hydrogens. Okay, so if we look at the problems here, if we start with A, we're going to draw this alkane carbon skeleton the same. And for hydrogen and palladium, we're just going to add two hydrogens, which you can draw in or you don't have to. With chlorine again, our skeleton stays the same. We'll add two chlorines across the double bond. For Br, we'll add two Brs. For HBr, we have an asymmetric alkene, so the hydrogen is going to go to the carbon with more hydrogens, which is this one, and our Br goes to the other one, and the same thing with the HCl. And you can leave the H off if you want, or you can draw it in so you know what is happening. And then with water and sulfuric acid, we'll get an OH here and a hydrogen on the carbon with more hydrogens. Okay, so you may have heard of margarine. and may have used it in place of butter. Butter is a solid at room temperature because it has no double bonds. It also contains stearic acid. While oils, which are liquids at room temperature, those have the double bonds present here, which raises the melting point so that it's a liquid at room temperature. And if you may have noticed that when you try to spread butter on toast after taking it out of the refrigerator, it's very hard to spread because it is a solid at room temperature and even more solid after it's been refrigerated. Substitutes or alternatives to butter, and these are spreadable right out of the refrigerator. So some of these have been made from an oil, such as corn oil or vegetable oil, where one of the double bonds has been hydrogenated. So the double bond has been hydrogenated, which means that the hydrogen has been added across the double bond to give it more butter-like consistency. So it's more solid at room temperature. It gets that semi-solid consistency. So adding that H2 hardens that oil a little bit. Hydrogenation also extends the shelf life of these oils, but this can create trans fatty acids, which are less healthy. So you might notice that some of the different peanut butters that you might eat have partially hydrogenated vegetable oil, which makes it so that it can be spread more easily. Other places that we might see alkenes are in polymers. And a polymer is a large molecule that's made of repeating units of smaller molecules that are called monomers. So PVC is made from polyvinyl chloride. They're made from repeating vinyl chloride units. So those alkenes that keep repeating. And you might have heard of polyvinyl chloride or PVC in different pipes. We have polyacrylonitrile, which is in different fabrics. Polyisobutylene is used in the balls for the playground. And we also have polystyrene, which you may know of it as styrofoam. So soft drink bottles, plastic bags, food wrap, even CDs that you may have heard of, Teflon and styrofoam, these are all made of synthetic polymers that have been created in the lab. So in a polymerization reaction, you have these monomers, and it undergoes a reaction and they join together to make a long repeating unit. We may also come across polymers in fabrics. So propene can make polypropylene, which in recent days you may have heard of polypropylene as they're used in different surgical masks and are good protection against COVID-19 virus. We also can see polypropylene in various mix of syringes. And then tetrafluoroethylene is another repeating unit that can be used to make polytetrafluoroethylene Teflon, which can be used in dental floss. You may also have encountered polyethylene terephthalate, or PET. These are in fleece clothing, carpeting, and plastic bottles. We have high-density polyethylene, or HDPE, which is different materials used for various plastics, or Tyvek insulation, outdoor furniture, sports clothing. These are often in plastics that can be recycled. Again, we have that PVC. There's LDPE, which is low-density polyethylene that's used in trash bags. We see that polypropylene again for furniture and also polystyrene. These are your different recycling codes that you might see on the plastic bottles.